Hi, folks. Thank you again for joining us for our second talk of today. Uh, I have the pleasure of introducing LoRA Zheng. Um, LoRA uh, uh, is a fifth-year PhD student in computer science at the University of Maryland, College Park, right here. She's supervised by Professor Ming Lin at the Gamma Group. Her research focuses on creating safer, more transparent, and generalizable autonomous driving systems by integrating simulation models with deep learning. She previously has interned with Waymo, Kitware, and NASA and has worked on projects involving both macroscopic and microscopic traffic mobility simulations. Um, in the fall of 2024, she received the Maryland Transportation Institute Fellowship, which has supported both of the projects that she's presenting today. So without further ado, Laura, please go ahead.
Thank you, Professor Xu. So going to play, you can see this presentation now. So yeah, cool. So hi, everyone. My name is LoRA Zheng. Thank you so much for the introduction as well. And here's welcome to my talk on who's driving the car, modeling driver personas for accurate behavior simulation in autonomous driving. Super grateful to have received the opportunity to present this ongoing work in the seminar series. So get into it. So here's a little bit about me. Maybe already mentioned in the introduction, but yeah, I am a fifth year PhD student in computer science at UMD, and I'm advised by Professor Ming Lin at the Gamma Group. And my research interests are in traffic behavior simulation and prediction. And I'm also interested in autonomous driving perception. So two very different parts of the autonomy stack there, but I'm nonetheless involved with both. And previously worked with Waymo, Kitware, NASA for internships in various projects in traffic simulation and document analysis, and was also received the Maryland Transportation Institute Fellowship. I'd like to also give a shout out, and they supported much of the work in this presentation because this work that I will be presenting actually started out as kind of like a class project that wasn't funded at first, and definitely started out very humble beginnings. So definitely shout out to them. And also little update on my status is that I'll be joining the simulation team at Waymo this fall full time. So yeah, that's basically on the horizon for me. And yeah, let's get started. So here's an overview on the talk and what kind of work I'll be presenting. So it's broadly going to be two themes. Where the first theme is, the first part is on user studies in virtual reality, and we're using this to investigate the relationship between driving style and pre-crash scenario behavior. And this is kind of in three parts here because, we're just beginning to like scratch the surface of how to like actually use virtual reality to assess driving behavior. So we do a preliminary study, and then we improve on that by making our own simulator. And then we redo the study on the improved simulator and collect the data set. And we'll be presenting that this summer at ICRA. So the second part is modeling driving style as a variable in deep learning. So this is kind of like the big data deep learning approach to driving style. So this is just an overview of what we're going to be going over. So for those of you who drive regularly, this map isn't new to us. So anyone who's driven on 495 knows that traffic congestion almost never clears up late night. And factoring additional time onto our routes to account for congestion is quite normal, at least in the DMV area. And yeah, so if we look at the societal cost for something as mundane as traffic congestion, it comes out to be pretty high for the individual. And this is quantified by TRIP, which is a transportation research nonprofit. They estimate that the average cost to a motorist in the DMV area is about 86 hours and $2,200 a year on just the traffic congestion. So it's quite expensive. Traffic sim is actually a very well-motivated problem. There's always reasons to be investigating traffic sim, whether it's for traffic engineering or just for purposes of investigating autonomy. But in this case, I'm interested in traffic sim for the sake of applying it to autonomous driving and being able to create better test scenarios for driving policies. Yeah. So just to motivate the question, what variables influence a driver's trajectory? So in traffic prediction or simulation, we usually condition it on several different variables to describe the multimodality of the future outcomes. So yeah, so first, we might imagine where the driver wants to end up, or, which is, I guess we'll call it intent here in red. And this is basically saying, like where are we trying to go? It's kind of like there's different hierarchical levels to it, but in general, it's where do we want to go? And next, we might imagine that the surrounding traffic and road layout is also a factor. So this is, we'll call this context. And this can involve anything from like the road shape to the like weather, the environment you're in, or what obstacles there are, whether they're dynamic or static. So this is just broadly context. And in this example, the two green vehicles split the lane change behavior into two different modes. So there's one option to change behind the green vehicles or one option to go in front. And both are very feasible outcomes as humans on the road. But in current benchmarks, which is based on distance metrics and it's often measured in units of meters, this discrepancy matters quite a lot. So currently there's no variable in current works that describe this discrepancy, at least in like deep learning modeling for traffic sim. So even though the intent and context are the same, the outcome is much different in the benchmark metrics. So we hypothesize that this difference in outcomes is best described as driving style. So that is if we account for the intent and the context, that the leftover variation in outcomes can then be modeled by like a third variable, which is driving style. So in this talk, I'm going to look at human factors from two different approaches. So first, we model behavior directly from humans with user studies. And so this is where we can directly query human subjects to annotate their driving style. And then we have them drive in a simulated environment to record the trajectories so that we can have the pairing between their driving style and their trajectories. And this seems very straightforward, but the really difficult question here is how do we design an effective study that provides enough immersion to produce realistic driving behavior? So in robotics, there's like this very well-known sim to real problem. Here, it's very much for the human factor. Does human behavior in simulation match human behavior in the real world? So this is what makes this approach particularly challenging. And the second approach is investigating behavior as a latent variable from existing data sets. So in this approach, we don't have access to the humans that we collect the data from. The large data sets are usually like these passive signals that we record from them, like their trajectories. We don't really have access to query these people. But we can collect them in like these data sets are essentially collected in large batches. So we could use modeling techniques to almost like cluster driving style as like an unsupervised variable and try to examine it that way. So this is like the big data deep learning approach. So I'm going to focus on this first part in the upcoming section. So why do we want to study behavior through virtual reality? So like, why not put someone in a real car? How do we get this paired data between driving style and trajectories? So we argue that driving style as a variable, it's most useful in edge cases. Actually, as if you've ever tried like a autonomous vehicle in production, you'll find that the autonomous driving policies actually work pretty well in general cases. If anyone's tried like the Tesla autopilot or like the Waymo driver, they actually work quite well for the general scenario. They're quite convenient and they seem to be very robust. So here we're really concerned about the edge cases, and the question is, how do we specifically get the pairing between driving style and trajectory? This particular pairing is not feasible in the real world whatsoever due to safety concerns. It could be super costly, first of all, just from like in general perspective. But we also don't want to subjugate people or users to risky scenarios. So we want to investigate this with immersive virtual reality simulations. So in the virtual reality studies, we want to fix the context and intent that we mentioned before. And we also want to prioritize risky scenario simulation. And so our work was inspired by previous work in crowd simulation that looked at diverging behaviors as a result of something called general adaptation syndrome, which describes the physiological response to stress that change behavior. So this is kind of like a very systematic approach to the fight or flight response when there's a stressor in the environment. And so we design our user study based on 37 pre-crash scenarios from the NHTSA pre-crash report. And these 37 scenarios cover about 99.7% of accidents. So this is quite inclusive. And on the right, you'll see like two examples of such scenarios from this NHTSA report, and they have some graphical representations of them. And so in our simulator, which I'll be talking about very shortly, we try to replicate these as closely as possible. So this is the preliminary work that I'll talk about on studying human factors with virtual reality. And so this is like a started out as a course project, and it was very difficult to kind of dissect how do we even begin designing a user study to collect data. So for this preliminary work, we had about 24 participants, most of which were recruited from the University of Maryland Computer Science Department population using physical flyers and digital advertisements. And in the first part of the study, we had users fill a questionnaire with briefing, consent form, the simulated sickness benchmark, and a driving style questionnaire called the multi-dimensional driving style inventory. And this is like a well-validated driving style questionnaire that's commonly used in traffic psychology literature. And then the second stage, we put users through a permutation of 4 scenarios, which we'll show you in the following video. And we made sure to collect 24 participants specifically because that's the total number of permutations of 4 scenarios that we have. We wanted to reduce the amount of scenario bias as people, for example, navigated a virtual reality environment for the first time. And so some details on our simulator implementation. So we actually use existing softwares for this. And the existing software we use is Driver, and this is a virtual reality wrapper on top of a driving simulator called Carla. And Carla was actually originally created for the use of as like an autonomous driving testbed. So it actually wasn't created for virtual reality user studies, and we'll get into that as a limitation later. But Carla has a ScenarioNet plugin, and this enables the customization of scenarios for diverse data collection. And so we started with this because it seemed like the ideal kind of software to get started with for a user study. There's some real limitations here in terms of realism. Also because it's a packaged software, there's very limited controllability we had over the scenarios. And this can also be kind of expensive and slow because the simulator simply wasn't built for user studies at first. So here is a quick demo. So our setup is, as I mentioned before, this started as a class project. So we kind of just like put together as many resources that we had on hand. But we simulated these 4 scenarios, and this is kind of what the user would see if you were to take the user study yourself. The spinning circle is basically like supposed to be an eye gaze tracker, but in this case, we had the autopilot on. So after we conducted the study, we first examined whether the assessed MDSI styles correlate with the actual driven trajectories. So we used the Pearson correlation test between the MDSI scores. So there's 8 factors, and each factor is like there's a scalar from 0 to 1 that measures the strength of that factor. And we look at the correlation between this score and the cumulative change in steering, throttle, braking, and in addition to curvature metrics. And so from the results, we noticed that the patient driving has stronger correlation to control input changes, and angry driving has higher correlations to curvature analysis. However, from this result, we noticed that the correlation was not significant enough overall in terms of these relationships, which is what we expected because we don't expect driving style to be a very simple linear relationship between these observable trajectory features and the actual driving style. So this basically just tells us that the relationship is actually a lot more complex. So this was kind of something we wanted to try for fun, where we just take a very simple trajectory regressor, so very shallow multi-layer perceptron, and we overfit each one network per scenario and we have each of them predict the driving style given a particular trajectory. So in these results, we expect that given like, for example, 24 samples, we expect the network to overfit. And so we plot the saliency of each trajectory here with respect to the classification. So basically what this is showing is the more intense the color is, the more important that part of the trajectory is to determining classification of driving style. So this is what saliency is. And so what we expect here is that because the data set's small, we expect to overfit, which means that there's memorization of the trajectories and their respective driving style pairings here. So we expect something more on the right with the control case is that like what we notice here is it's very uniform. It seems like the entire trajectory is being used to somewhat predict the style. And so this is more so what we expected for everything, but what we noticed in the jaywalking pedestrian scenario was that there was a much more structured pattern for saliency when it comes to driving style prediction. And this comes in like just a small time window before before crossing the line of where the pedestrian's crossing the road. So this is like a more noticeable pattern in terms of saliency. And this might hint at us that, what we were discussing with the general adaptation syndrome earlier, is that having a stressor in the environment could be a factor that makes driving style more observable in trajectories. So this is a cool little experiment that we tried with our small data set. And yeah, so in terms of limitations, most of the limitations stemmed from hardware and software. So of course, there's very little we can do about the hardware. We're kind of limited by, we were using the best VR headset we have available to the lab. And the software is also difficult to modify because it's kind of like this packaged wrapper. And then there's also the Carla simulator. And getting into that from the source code side is quite hairy. So this kind of reduces our ability to properly improve things like frame rate and the diversity of scenarios. And Carla also has a lot of features that's important for autonomous driving testing, but not so important for user study administration. So the other aspect is that traffic simulation is not realistic in driver, simply because the traffic manager is based on Carla, and just intuitively, the traffic simulation was unrealistic in the sense that every driver drives extremely slowly. And so it wasn't realistic in that aspect. So as a direct extension of this work, and with the help of a great team of students, we created this new VR traffic sim for data collection from scratch in Unity. And this integrates both virtual reality optimizations in addition to Sumo traffic simulation. And this simulator has an expanded number of scenarios. Sorry, I'm just going to mute this really quick. To 8. So previously we had 4 and now we have 8, and all of which of these are based on the NHTSA pre-crash scenario report. So yeah, this is just kind of like a sneak peek as to what the simulator looks like through the VR headset. And of course, this is all using a very low cost setup on our lab side. And we ran another user study to compare this simulator to the one we used initially in the preliminary user study. And we saw good improvements across a bunch of different factors, including realism, ease of use, and overall user experience. This is pretty neat. And so we then took this simulator and we reran the user study design from the preliminary work on this updated and more improved simulator. And this time we also expanded the number of participants to 100, and we recruited them in the same fashion from around campus with flyers and whatnot. And this data set disk is a byproduct of that user study that we'll be releasing on our project website. And this will also be presented at ICRA 2025 this summer. This dataset includes Sumo traffic annotations, sensor data, simulator replay logs, and all that. Also, we integrated this data set with common trajectory prediction frameworks, so you can also use it alongside data sets like Argoverse and Waymo and stuff like that. So yeah, this is neat. And here's also a little sneak peek of the scenarios, and this is also without the headset. So you'll see that there's some sort of like risk involved there in every scenario, and we planted some control scenarios in there for the user study, which involves no risks, or at least no risky actors. And so really quickly, try to get through this next part pretty quickly because it's ongoing work. We're on the part where we're trying to model from big data or with deep learning approaches for driving style. So this work, we'll call it polysona because we're trying to do parameter efficient persona conditioning for traffic sim. This work is ongoing, as I mentioned before, and I'm just going to very briefly mention what we're trying to do here. So again, we're trying to model driving style with interpretability and controllability, and we also want to choose outcomes in the same scenario under different styles. We want to simulate different outcomes, and we also want it to be efficient and not lose base model performance. And also, we want to be able to generate novel scenarios with simulation. So here's our proposed approach. And as you see here, the contribution is mostly on the top half. And we in the top left, we first use context embeddings to learn a latent variable here. So we use this through like classical VAE modeling. Basically, just want to take the context embeddings from the encoder and predict some sort of like latent variable vector there. And then we want to use this discretized latent variable value to select an acceleration scaling factor. So we want the latent variable to directly have to do with something observable like acceleration. And then finally, we also want to use this latent variable as a routing function to select specific LoRA modules for style-specific adaptation. So here you see different, like for example, 8 different adapter modules. The vision here is that each one would represent one component of, for example, the MDSI, like angry, risky, careful, patient. And then we use those adapters, just tack it on to the decoder of any like sort of encoder decoder trajectory simulation model, and then be able to roll out and change the outcome according to such style. So here is some preliminary results from this. So here you might see that we have different styles. These are latent variables, so there's not an inherent intuitive style assigned to each, but you can see we did assign a prior probability to each one. So here on the left, you see 0.3, then we have 0.6, and the most rare case on 0.1. And some emergent behavior that we saw is in this, for example, this example shows in the rare case that is supposed to occur most infrequently, this driver who seems to swerve and overtake another vehicle aggressively. Also note that these results are open loop, so it does run off the road, but it doesn't. It's not supposed to. It's supposed to be reevaluated at certain intervals. So that's basically all I have for this current work. And this wraps up my talk for this seminar. And I just wanted to thank everyone for coming out, and also do another shout out for the Maryland Transportation Institute Fellowship again, because they did support me for a lot of this work. And now I'd like to open the floor to questions.
Thank you so much, Laura. So we have one question so far. So how well do participants do even when there are no risks presented in the scenarios? So, for instance, like DMV drivers are notoriously known to be a bit reckless. So,
Mhm.
if some drivers would be even more reckless in a VR environment where there are no consequences to real life crashing?
Yeah, so this was I think I have some extra slides. So this is actually a really good question because we're quite worried about, the first thing to think about is whether or not VR simulations are reliable data points. And so we haven't entirely answered this question yet, but we did do some sort of simulator evaluation in terms of immersion. And so this is on this these numbers are on the preliminary one with driver. So this is not on the updated simulator that we have. But essentially, I would say from a intuitive explanation standpoint, I don't have numbers on this. I did observe that it was not so much that people would drive more recklessly because they knew they were in virtual reality. It's more that for a lot of our users, it was their first time specifically driving in virtual reality. So there was this novelty component that I think if there is a sim to real gap, it would be more attributable to the novelty component of driving with a headset on, rather than like being able to drive recklessly with no consequences. But in the control cases, I did notice that people, for the most part, seemed to drive lawfully. And we also did have compensation for this user study, so there was somewhat of an incentive to, try to give us a good data point there. But yeah, just from an observational or qualitative standpoint, I didn't notice that people were trying to drive recklessly by any means.
Mhm.
But some interesting things. Some participants, a lot of the participants did not use the mirrors, and I think that's not a realistic outcome of our data set. I'm sure that people use mirrors in the real world, so the lack of the use of the mirrors was really interesting. And also from a rendering standpoint, mirrors are quite expensive to render. So we did increase the computational cost of running the simulator by including mirrors. So it was really surprising that people did not end up using them.
Did you notice, I'm just curious, a
Yeah.
difference between people who have experience with video games in VR versus people who don't?
Yeah, there was so for example, we had just general qualitative conversations and like short answer responses with folks. There were some people who were extremely experienced with, like, for example, racing sim games in VR, or just racing sim games in general, because we did have a racing game set up. Like we had like the Logitech wheel, more so like what people might have at home if they were into driving games. What I did notice for that was the folks who had experience there, they did tend to have more grasp on the controls and more experience there. But their criticism on the immersion or the quality of the simulator, it tends to be much lower compared to someone who hasn't used VR before, who hasn't used like a driving setup. Those we saw that their evaluation of like how nicely they felt the simulator was higher than those who have experience. So there was a stark difference there, at least.
Interesting, great. Are there
Yeah,
any other questions? Okay, well, thank you so much, Laura, for your time. This was great.
yeah.
And thank you all to our audience for joining us. Oh, wait, hold on. I think there might be one more question. Okay, we do have one more question. From Tiffany. I'll just read it out. I thought it was interesting how you can use both user studies and latent variable modeling for driving style. Do you think it would be useful to combine them, or do you have any insights on how one method can help research on the other?
Yeah, so we have two approaches here. And so let me see. So in the first half or first portion with the user studies, we did introduce a data set. So let me see here. We have the data set. It's called DISC. And here, what was really cool was we had the driving style and trajectory annotations. So we have somewhat like of a trajectory data set, and we have their paired annotations. But as you may have noticed, the latent variable modeling doesn't really make use of these driving annotations. So actually, we're planning to incorporate that as some sort of hint for the latent variable in the future work. So, and not just like the next future work after this one, but what we're looking to do is in this current work, once we have like a reasonable latent variable modeling procedure, we want to use the driving styles from our data set, which represent like edge case scenarios. We want to be able to find a way to identify similar scenarios in these large scale data sets from a trajectory standpoint. So we want to look for example, close call scenarios that might be like a needle in the haystack in these large data sets, and then be able to like use the paired driving style annotation as some sort of like guidance for those more rare scenarios in the large data sets. So that's definitely something that's on our radar. And that's also how we're going to bridge the two works together.
Great, wonderful. Thank you so much. Okay,
Yeah.
Thank you, Laura, again. Thanks to our audience for participating, and we will see you all at our next seminar. So have everyone have a great Friday.
Thank you.